Hello, good afternoon, everyone. Let's start the tutorial now. Today we will have a super short tutorial. We are starting to talk about basic number theory, and last time we have introduced some interesting results about the greatest common divisor. So in particular, we have introduced the following results. So suppose that x and y, they are positive integers. Then we know that the following three facts are true. First of all, the greatest common divisor of x and 0 will always be x. It is because x and 0 are both divisible by x. So x times 0 is 0, x times 1 is equal to x. Is that okay? And there is no larger number that can divide x and 0 properly. So GCD x of x and 0 is equal to x, and the GCD function itself is a symmetric function. So the greatest common divisor of x and y is the same as the greatest common divisor of y and x. And one more is the greatest common divisor of x and y is the same as the greatest common divisor of x with y modulo x. So y modulo x is taking the remainder of y when it is divided by x. Now, based on these three facts, then we can design the famous Euclidean algorithm to find the greatest common divisor of any two numbers. So suppose that we have x and y are like this example. So what we are going to do is we want to find the greatest common divisor of 1, 4, 1, 7, 2. This is x here, and 2, 3, 4, 6. This is y here. So what we are going to do here is that because these two numbers are very large, so we want to simplify the problem a little bit. So we want to make the numbers smaller. So one way is we want to replace this large value. Let's say this is an x value. Replace it by x modulo y. Okay, so we are deducting some multiples of 2, 3, 4, 6, so that after doing this, we have this is at the remainder. So when 1, 4, 1, 7, 2 is divided by 2, 3, 4, 6, we get a remainder of 96. And now, the original problem is now transformed. So originally, we want to find the greatest common divisor of this number and this number. And now suddenly, we make this number much smaller to find the greatest common divisor of 96 with 2, 3, 4, 6. So after this step, we can do the same thing again. So this time, we want to make this number smaller. So what we are going to do here is we want to divide this number by 96 and find the remainder. So the remainder here will be 42. So after these two steps, original problem is now transformed to a much smaller problem, 96 with 42. So indeed, if we are good at calculation, so we can immediately find out that the greatest common divisor of 96 and 42 is equal to 6. But nevertheless, let's continue with the process. So this time, this is a larger number, so we want to make the larger number smaller. So we divide the larger number by the smaller number and find the remainder. Divide 96 by 42, we get the remainder 12. Now we have 42 and 12. We divide 42 by 12 and get the remainder 6. And 12 and 6, we divide 12 by 6 and we get the remainder 0. So in that sense, originally we have these two to find GCD, and after that these two to find GCD, 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 and after that these two to find GCD. And with one of them becoming 0, so we know that the GCD is equal to 6. So in that sense, we have computed the GCD using this idea. Okay, so this method is called Euclidean algorithm. It is already known by the time of Euclid. Now, in addition, when we are in the lecture, we have also mentioned this interesting fact. The greatest common divisor of x and y is actually, it is always equal to the smallest positive linear combination of x and y. So this linear combination means that it is equal to some integer times x plus some integer times y. So these integers can be positive or negative. So we consider among all the possible integer, let's say a, and integer b, let's say, so we want to consider all the possible ax plus by and find out which one achieves the smallest possible positive value. Okay, so in that case, it turns out that it will be equal to exactly the GCD of x and y. So how can we find out this a and b? What is the linear combination of x and y such that we can get it to be the GCD of x and y? It turns out that we just need a very small modification of this Euclidean algorithm. This is what we are doing here. So sometimes people call this the extended Euclidean algorithm. So we do not just perform the Euclidean algorithm alone, but we also keep track on some extra information. So 14172 can be expressed, this number can be expressed as a linear combination of the original x and y. This must be 1 times x plus 0 times y. Is that okay? So 14172, I will use this vector 1, 0 to represent it is equal to 1 times x plus 0 times y. Is that okay? And similarly, 2, 3, 4, 6 will be represented by this vector 0 and 1. Is that okay? Now, when we perform the division and also the modulo arithmetic, so when we do this, we find that we are deducting 6 times 2, 3, 4, 6 on the left-hand side. So 6 times this one is equal to 6 times 0, comma, 6 times 1. So this 14076, it turns out that it must be equal to 0, 6. Is that okay? And after that, we can get the remainder. The remainder will be equal to this one minus this one. So it is equal to 1, 0 minus 0, 6. 1 minus 0 is 1. 0 minus 6 is minus 6. So we will see that 96 itself is equal to 1 copy of x minus 6 copies of y. So 96 is like this. So what is 2304? 2304 is 24 times of this 96. So it is going to be 24 minus 144. We do this again and again. So we are actually keep tracking on every possible term that appears in this method. And then for each term, let's say the final term here is 6. 6 is the greatest common divisor. We will immediately know that it is corresponding to the vector minus 171, 1033. So in that sense, 6 can be expressed as minus 171 times big X plus 1033 times big Y. Is that okay? And interestingly, you can also see that 0, of course, it is equal to 0 times x plus 0 times y. But we also have another alternative. So 0 is also equal to 391 times big X minus 2362 times big Y. Okay? Now, this is actually the purpose of this tutorial, to introduce the Euclidean algorithm and also this extended Euclidean algorithm. And one more thing that I want to mention is that Euclidean algorithm is very fast. So how many steps are we going to do here? So if you watch carefully, so this is the original value of x, this is the original value of y. Now, no matter which kind of y that we are talking about, if y is very large, then let's say y is more than half of x, then the remainder will be smaller than half of x because we are going to deducting at least 1 copy of y. So it is smaller than half of x. On the other hand, if y itself is smaller than half of x, then what will happen? Then we will also have the remainder to be smaller than half of x. It is because the remainder must be smaller than y. So in that sense, after one modulo arithmetic operation, we will find that the original value of x is now shrink into a value. This is at most half of its original value. So this is also at most half. So by using this idea, we will see that we will need at most log of x plus log of y step to find out the greatest common divisor. So log of x plus log of y, the base of this one is 2. Actually, we can have a slightly tighter analysis. So here we are using that this is like log of 2, but then we have log of x plus log of y. So it is like 2 times log of x, something like this. But in fact, we can have a tighter analysis. So how can we make it tighter? So we do the opposite thinking. Okay, we want to find out, given some x and y, how small x and y will force us to have n steps of modulo operation. Now, if x and y is like 1 and 0, then we don't need to do anything. 0 modulo operation, right? If x and y, they are both 1, then we will have 1 modulo operation. Is that okay? And then so in that sense, we can use this idea. In order to have 2 modulo operation, we need to have something like 1 and 2 in order to force us to have 2 modulo operation. In general, if we want to have n modulo operation, we will need to have at least one of them is the Fibonacci number, let's say Fn, the other is the Fibonacci number Fn plus 1. So in that sense, what does that mean? It means that if we need to force us to have n modulo operation, then we will need to have at least certain value. But on the other hand, if x and y, they are not as large, then we can't have that many modulo operation. So in that sense, somehow by using this idea, we can argue that Euclidean algorithm runs in log of x number of steps, where the base of this log is the golden ratio, the golden ratio 1.61828, something like this, plus some little constant. So this is slightly better than 2 times log of x base 2. Okay, if you are interested in showing why this is correct, you can try it yourself. This can be easily shown by using induction. So I think that's all for today. Yeah, I hope you like it. So this Euclidean algorithm is very useful, especially in the next topic that we are talking about, the modulo arithmetic. Sometimes we need to find out something called the inverse of a number. Okay, so that's all for today. So let me check if you have any questions. Let me see. If no, then yeah, that's all. Thanks all. Okay, and see you on Thursday. Bye bye. Thanks.